You're watching a Channel 98 NBISD TV production.
Ahoy there, me hearties. Welcome to Deja Vu. It's Algebra 2. I am Captain X-Beard, High Commander of the High Seas, and amateur mathematician, you know. You think those gold coins count themselves? You're probably wondering where your usual host, Mr. Corpy, is, aren't you? Or maybe you're not, huh? Well, I've kidnapped him, and I've taken over the show. After all, I am a pirate. That's what we do. Stick around for today's episode. I'm going to try my hand at teaching you something about matrices, leading you on the fantastic voyage. So download those worksheets from the district website. And grab a pencil and a sword if you have one. And I guarantee if you stick around, you'll be hooked. Let's get to the math. All right, Lesson 8, Introduction to Matrices. Now, as you know, we live in an age of information. It's all around us. It's at our fingertips or at our hook's tips. Now, with all of this information, it's very important to be able to interpret and make sense of all of it. Now, one mathematical way to arrange all the information is in a rectangular array called a, let's see, I'm right-handed here, so this might be a little challenging, but I'm up for a challenge. It's called a, you know what, I'm going to have to give this to Mr. Corpy. I'm going to have to go untie him and let him do the lesson. This just will not work. Okay. Thank you, Captain X-Beard. That was very generous of you. Yeah, as he was mentioning, we do have a lot of information, and one mathematical way to make sense of it all is in something called a matrix. Not the movie, the mathematical matrix, which is just a simplified way to organize information. It's a rectangular array. An array is just short for arrangement. Let's look at this little sample right here. We have the collected spoils by the rival pirates in the high seas, and we're going to measure it in gold coins. So we have two pirates here. We have Captain Y and X-Beard. You've already met him. And in the month of June, 205 for Captain Y, 358 that they've stolen, or pirated as they call it. They think steal has such a bad connotation. In July, 157 and 501 for X-Beard, and in August, 169 and 678. So X-Beard is a better pirate than Captain Y. But in the table format here, it's very easily arranged. We can make sense of it pretty quickly. Now let's make the jump to a mathematical matrix. A mathematical matrix is going to contain the same information, but we're not going to have the titles on our columns or on our rows. We're just going to take the numeric data, like the 205, 358, and we'll arrange it in columns. This has columns. We have 3 columns there, and we have 2 rows of information. Now we do lose the fact that everything in here stands for something, but in the context of the original problem, this is a much more systematic, efficient way to list the numbers. And we always put brackets to include our arrangement or our array, and we also give it a capital letter. In this case, a P is a good choice because it deals with pirate information. And there is Captain Y. You've already met Captain X-Beard. So a matrix is just an ordered set of numbers listed in a rectangular form that is represented by a capital letter. Let's look at this other example here. We have really no context of what these numbers represent, and that's okay, but it is a matrix. We're going to let A, capital A, denote this matrix right here. Now notice that it's a little bit larger than the last one. It has, let's see, 1, 2, 3, 4 columns, and 1, 2, 3 rows. So we can say that its dimension, which is our relative size of any matrix, is a 3 by 4, or simply that it's a 3 by 4 matrix. And that's how we are going to actually name each matrix. we're going to name it by the number of rows by the number of columns. Every single time, rows by columns. So if you just remember RC, RC is row then columns. It's not CR, it's RC. So again, we have 1, 2, 3 rows. Those are the horizontals. And we have 1, 2, 3, 4 vertical columns. And so this again is a 3-row by 4 column or 3 by 4 matrix. Okay, so that's how it can refer to the size, and we call it the dimension. Now each value, each number inside this matrix has a specific name as well. We call it an entry. Okay, so we have all these entries in here. We actually, in this case, are going to have 12 entries. It's a 4 by 3 rectangle. And if we're trying to refer to a specific entry, we talk about the address of the entry. So each entry has an address. And how are we going to refer to an entry? What does the address look like? Well, we're going to use, first of all, the lowercase letter of the capital name of the matrix. So every entry in here is going to have a lowercase a followed by a subscript that is the row again and then the column, and we usually separate it by a comma. Here's the same matrix, and we have Captain Xbeard's pirate ship over here. We want to know what address the 3 is in here. Okay, well notice then we want to do row then column, so I'm going to have to put a lowercase a because it's big A, and the row that it's in is the 1, 2, 3rd row horizontally, so it's 3, comma, and it's in the very first column. So the 3rd row and the first column is a 3, comma 1. So we say that a, little a, subscript 3, 1 is the number 3. Okay, so that's how we refer to the specific locations in a matrix. It's very ordered, it's very structured. And we structure it by rows and then columns. Now, if a matrix A has the same number of rows and columns, unlike this one, this was a 3 by 4, we call it a square matrix for obvious reasons. It would be a 3 by 3 or a 4 by 4. And in that square matrix, we say that the entries that are of the form A, subscript II, where I is just 1, 2, 3, blah, 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 like the element A 1, comma 1, or A 2, comma 2, or A 3, comma 3, that's going to be the entry in the 1, 1 position, or in the 2nd row, 2nd column, 3rd row, 3rd column. Those are going to be like this right here. We have a 3-row by 3 column matrix. We're calling it A again. And because it is a 3 by 3, notice that it makes a nice little square. There's 3 squared, or 3 times 3, 9 entries in here. Well, these elements that are in the 1, 1, 2, 2, 3, 3 position are along the diagonal. So we say that those are the diagonal elements in a matrix. Now, you're probably saying at home, what about these numbers? These are also along a diagonal. That is true. But we're looking at the ones that start in the top left corner only for a square matrix that come from the top left to the bottom right along that diagonal. Those, by convention, we call the diagonal elements. Now, what about a square matrix that has 1 row and 1 column? Are you thinking about that? For instance, here we have a matrix. We see the brackets. There's a 5. There's 1 column, and there's definitely 1 row. So that would be a 1 by 1 square matrix. Well, remember the whole purpose of a matrix is to organize a lot of information. If we're just trying to organize a single number, that's probably too much notation. And so we can actually refer to the 1 by 1 matrix, 5, to be simply the number 5. There's no need to organize it in any higher structure. 5 is a 5. Now we have a couple of special types of matrices. The first type is called a row matrix. A row matrix is basically a matrix with only 1 row. So here we're calling it R. Captain Xbeard liked that. It has only 1 row, and notice it has 1, 2, 3 columns. So we would say that this is a 1 by 3 matrix. We could have multiple columns. We could have 4 columns, 10 columns, 100 columns. But if it only has 1 row, we call it a row matrix. So it's going to be a 1 by something. On the other hand, we have in this one, we'll call it matrix capital C, we have only 1 column. Well, that's going to have a special name called a, you guessed it, a column matrix. A column matrix has 1 column and as many rows as we want. So this would have a dimension of 3 rows by 1 column. So that's a 3 by 1. We could have a 4 by 1, a 5 by 1, or whatever. As long as the number of columns is 1, we still have our column matrix. Now, one of the advantages to using matrices, getting rid of the column headers and just looking at the numbers in a systematic sequence, is because we can define arithmetic operations on the matrices. And those arithmetic operations, much like we do on our numbers, can be performed in a systematic process. The other reason that matrices are nice is because we can actually program. We could tell computers or calculators a very set of structured commands that allow them to perform operations on the rows and columns. So it's a nice way to systematically do calculations for large sets of data. Now, some of the things we're going to look at today are addition and subtraction of two matrices, and we're also going to be looking at multiplication by a scalar multiple. And a scalar multiple is just like the number 5. We can multiply a number times a matrix. And that's what we're going to do right now. So how are we going to add or subtract two matrices? Well, let's call them capital A and capital B, two matrices. In order to add two matrices or subtract two matrices, it doesn't really matter, they must have the same what? Well, they must have the exact same dimension. They have to be at the same size, the exact same size. And the reason that is because to perform the addition or subtraction, we simply add the corresponding entries. And if they're not the same dimension, then we're not going to have a one-to-one correspondence from a row-column position to a row-column position. There's going to be a dimensional mismatch. So they have to be the exact same size, and we'll add and subtract the corresponding entries. Now, to multiply by a scalar multiple, all we have to do is distribute that number to each entry through the operation of multiplication, just like we would with numbers. So let's put this to the test. We have matrix capital W, which is a square 2-row, 2-column matrix, so that's a 2 by 2. We have matrix Y, which is a 2-row, 2-column, so that's a 2 by 2. We have matrix X, which is a 2-row by 1, 2, 3 column, so that's going to be a 2 by 3. And then we have matrix Z, which is a 2-row by 1, 2, 3 column. That is also a 2 by 3. So W and Y have the same dimension, so we're going to be able to do operations between the two. X and Z have the same dimension, so we're going to be able to do operations between those two. So let's try this. Let's try adding matrix W to matrix Y. It works because they're exactly the same. So how do we add two matrices? Well, we will add their corresponding positions. So let's look at the first row, first column of W. It's a 3. And we add that to the first row, first column of Y. So 3 plus 1 is 4. And now we move on. First row, second column is a negative 2. And we get the first row, second column is a 4. So 4 plus negative 2 is 2. It doesn't matter how we fill in our resultant matrix. I can jump around so long as I'm adding the corresponding parts. Let's do the second row, second column. Second column is 0. Second row, second column is 3. 0 plus 3 is 3. That's my new 2, 2 position. And then I'm left with my second row, first column. So second row, first column, that's a 1. Second row, first column is a negative 2. 1 minus 2 is negative 1. And we get this as our resultant matrix. All right, let's try X minus Z. Well, I can do it because they're the exact same dimension. So I'm going to have to subtract now corresponding locations. So I'll take 4 minus 2 is 2. 7 minus negative 2 is 9. 2 minus 3 is negative 1. We're going to want to leave enough space in between here so that it doesn't look like it's one number, 290 negative first, which doesn't make sense. But we don't want to put them too far away either. I like to start in the top left and work straight across, just as a matter of convention here. Now let's do the bottom. I'll do 5 minus 1, X minus Z. That's going to be 4. 1 minus 0 is 1. And negative 1 minus 4 is going to be negative 5. And so we have this as a resultant matrix. Well, let's do X plus Y. That's going to be this matrix here, which is a 2 by 3, plus Y, which is a 2 by 2. Oh, it's not going to happen. I'm not going to have a one-to-one correspondence in rows and columns. So this one we cannot do. There is a dimension mismatch. It does not work. All right, so we can't always perform the operations, but when we can, we want to do it correctly. Now this one here is the first time we're going to bring in our scalar multiples. This is 3 times the matrix Y minus 2 times the matrix W. So what I want to do is first create this matrix and then create that one. And then I will do the subtraction. So how do I get 3 times Y? Well, I'm going to take the number 3. I'm going to multiply it by every element in Y to get my new element. So here we go. 3 times 1 is my new 1, 1 position. That's 3. 3 times 4 is 12. That's my new 1, 2 position. 3 times negative 2 is negative 6. That's my new 2, 1 position. And 3 times 3 is 9. That's my new 2, 2 position. Minus, I'll do the same thing here. I'll take the 2 and multiply it by each entry in the W to get my new ones. So 2 times 3 is 6. 2 times negative 2 is negative 4. 2 times 1 is 2. And 2 times 0 is still 0. So I have to have an intermediate step here. Now I have two 2 by 2's, so I can subtract corresponding entries to get my final answer. 3 minus negative 6 is negative 3. 12 minus negative 4 is 16. Negative 6 minus 2 is negative 8. And 9 minus 0 is 9. And so notice if I have two 2 by 2's to start with, I'll end up with another 2 by 2 because I've just added corresponding entries.
Ah, that Mr. Corpy's doing a great job, isn't he? He may not have to walk the plank at the end of the show after all. We're going to take a quick break. We are. But don't go away. You better be there when we get back. Here's something to ponder while you're gone. How did the pirate student like his math homework? The answer when you return, and you better be here!
I smoked weed, and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot at dying out there in the real world. Driving hard to the rim, ice skating with a girl. Now you want to keep yourself alive? You go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
Mom! Mom!
What?
You can't find Ichabod.
What?
You don't have to be perfect to be a perfect parent. There are thousands of teens in foster care who would love to put up with you.
Welcome back to Deja Vu. It's Algebra 2. I'm Captain X-Beard today, pirating the ship that is Mr. Corpy's. He's my first mate today. He's doing a fine job. Did you think about the question? How did the math student like his math homework? He liked it nice and hard. Oh, I'm so good. Let's get back to the math.
All right, now with any arithmetic operation comes some property of equalities, things that we can actually do within the realm of the operations that are legal maneuvers. Here are some of them. We're going to have a verbal column, a numeric column, and an algebraic column, and we'll look at each of them. So remember, for numbers, we had something called the commutative property. Well, we have commutative property for matrices as well. Matrix addition is commutative. So here's the numeric version of it. If I have two matrices like this, two 2 by 2's, and I add one plus another, that's going to be equivalent to switching their order, this one plus that one. And the reason is because we're just adding the corresponding columns. So if I looked at this in the 1, 1 position, I have 7 plus 1 would be my new 1, 1 position, whereas over here, my new 1, 1 position would be 1 plus 7. So since addition itself is commutative, and I'm doing that in each of my corresponding entries, then the matrix C itself has a commutative addition property. And algebraically, if I just call the two matrices matrix A and matrix B, then that's just capital A plus capital B equals capital B plus capital A. Commutative. We could switch them around. We also have the associative property of addition, which says we can add the 2 or 3 matrices in any combination, and we'll get the same result. So if I have 3 matrices here, I can add the first 2 together to get a result, and then combine it with this one. So let's look at this position here. I got 2 plus 0 is 2. If I add that to this, I get a 5 plus 2, which is 7. So I'd get a 7 in my 1, 1 position. And let's see what we get over here. This has the last 2 grouped first. So 0 plus 5 is 5. And I'll take that result, 5 plus 2, and of course I get 7. So because arithmetic itself is associative, so is matrix addition. And symbolically, then the sum ABC is A plus B first plus C, or A plus B plus C first, the associative property. Well, now we have something called the additive identity. And in addition, the additive identity is that number that we can add to any number and leave it unchanged. And that number is 0. Well, matrix addition also has an identity element. It's the 0 matrix. And the 0 matrix is going to be a matrix that has 0 for every single entry. That's the exact same dimension as the one we're adding it to. So in this case, if I'm starting with a 2 by 2, the identity, or the 0 matrix, the 0 matrix will be another 2 by 2 with zeros everywhere. And notice that if I add all the corresponding entries, 7 plus 0, 7, 2 plus 0, 2, 3 plus 0, 3, 4 plus 0, 4, I get what I started with. And so this is the 0 matrix, which is the identity element for addition. And finally, we have the additive inverse. Now in arithmetic, to obtain the additive inverse, it's the number that we have to add to any other number to get the identity element, which is 0. So 5 plus negative 5 is 0, the identity element. And so it's just the opposite of that number. Well, a matrix also has an additive inverse. So if I start with a matrix like this, which is a 2 by 2, the additive inverse, which is this right here, is nothing more than every entry that is the opposite of the corresponding entry. So if I have a 5 here, that's going to be a negative 5. So that when I add them together, I get a 0. Negative 2 is here, so I have to have a positive 2 there, so that when I add them, I get a 0. And we'll go all the way through that way. And because I reached my 0 matrix, then this is the additive identity. So an opposite entry in each corresponding point. We can write that mathematically like this. If two matrices, A and B, add to 0, then we know that A and B are additive inverses of each other. We can also use this notation. If I put A to the negative first power, we read that as A inverse. And that'll come up on a future episode. Let's do a little bit of algebra with the matrices now. What we want to do is we want to solve for A, B, and C in the following matrix equation. Look at that. I've got 2 times this matrix plus that matrix equals this matrix here. And I have some unknowns in my entries. I have an unknown A, an unknown B, and an unknown C. Notice that these are all 2 by 2 matrices. So I can do the addition, and I'm going to obtain another 2 by 2. Well, notice this little 2 is out here. So what I need to do is first create my matrices. I'll distribute the 2, and I get a 6. I get a 2A. I get a negative 4 and a negative 16. Plus, the other 2 I just have to rewrite. Very patiently rewriting. And then over here, this one stays the same. So there was just one thing to do, and now I'm ready to go. What I want to do is I want to create 4 different equations that are going to be the corresponding locations. So let's look at the 1, 1 position. It's going to be 6 plus 11, right there, equals 17. Well, there's no variables there, are there? But what is 6 plus 11? 17. So that's a true statement. That's nice. Let's look at the 1, 2. The first row, the second column. First row, second column. That's going to be 2A plus negative 4 has to equal negative 10. I have a little linear equation now, so I can solve it. That means 2A has to equal negative 6, and if I divide through, I get A equals negative 3. So I found one of them. We'll proceed in the same fashion. Let's do the second row, first column. Second row, first column is going to be negative 4 plus B equals 9, right there. And I have a little linear equation, so B equals 9 plus 4, that's 13. And then finally, my last one down here, I'll look at my 2, 2 position, and that's going to be negative 16 plus 12 equals C. Well, that one's easy to solve for. I get C equals negative 4. So there we go. We have solved for A, B, and C just by doing the matrix addition in the corresponding columns. Now it's time for
Deja Review.
All right. We're going to review everything here in the context of another pirate example. I'm under duress here from Captain Xbeard, who's making me do this. Okay. I do not want to walk the plank. I do not want to swab the poop deck. I just want to get the heck out of here. Let him go back to his high seas. Well, he gave me this example. We have a table here that basically is the cost of pirate clothing in dollars. We have shirts, pants, and hats. And here's what we could do. We could buy any of those 3 objects. We can buy them dirty without holes. We can buy them dirty with holes. Or we can buy them dirty with holes and stains. Ho ho! So the best of the three would be, I guess, dirty without holes, and that's why, if you notice, that's the most expensive column. All right, so what we want to do is display this as a matrix, call it matrix C for clothing. So here we go, matrix C. We're just going to write all the information without the column headings. So it's 23, 21, 15. I don't have to put the trailing zeros. Then I have 14, 13, and 9. And then finally I have 11, 9.5, and 6. And there's the matrix. What is it? It is a 1, 2, 3 by 1, 2, 3. So that is a square matrix. And we have our diagonals right here, 23, 13, and 6. Okay, what are the dimensions of C? Well, I've gotten ahead of myself there. It is a 3 by 3, 3 rows, 3 columns. What is the entry in the 3, 2 position? Little c subscript 3, 2. What is the entry? Well, let's come back up here. 3, 2 is third row, second column. So 1, 2, third row is the bottom. Second column, there's 1, 2. The intersection of the third row and the second column is 9.5. So C subscript 3, comma 2 is 9.5. What does it represent? Well, let's come back up here. It represents the cost of a dirty hat with holes. So a pirate can buy a dirty hat with holes for only $9.50, or whatever that translates to in gold coins. I hope they don't need change. All right, let's answer another question. What is the address of the entry that is 14? Well, where's 14? It's right here. Okay, so 14 is going to be where? It's a capital C, so I have to use a little c. And it is in the 1, 2, the second row, the middle row. So that's 2, comma, which column? Well, it's the first column. So 14 is in the 2, 1 position. And that's its address. And that represents a pair of dirty pants without holes. Good to know. Now what we want to do is we want to use the scalar product to find the total price if there's an 8.25 surcharge on each item. Yeah, even pirates get charged surcharges, okay, especially if they don't have their sword with them. Well, how are we going to do that? We're going to have to take the original cost plus add the surcharge to it. Well, 8.25 as a decimal is 0.0825, and we have to multiply that by the cost of the item and add it back to the cost of the item. It's like tax. The cost of the item plus the amount of tax. Well, I can add those. Those are like terms. So that's really 1.0825 times matrix C. So all I have to do is come through and multiply each entry, each of the 9 entries in here, by 1.0825, and I'll get the P. I'm going to call it P for price, is going to be this. I have the numbers here. This is where a calculator is helpful. I get $24.90, $22.73, $16.24. That's along the first row. And then I get $15.16, $14.07, $9.74, and then finally $11.91, $10.28, and finally to buy a dirty hat with holes and stains after my 8.25% surcharge, it's going to cost me $6.50. Or I can just steal it like a pirate, right? Well, remember, math is power.
Arrgh. So what a show we had today. We learned a little bit about matrices, a brief introduction. Now I'm going to insist, because I like them so much, that Mr. Corpy spend the next couple of weeks talking about matrices. So if you want to do well, you better learn the basics first. And practice, practice. Yes, you will. And I guarantee, as hard as it might seem eventually, with Mr. Corpy, pirate or commanding the ship, the mathematical voyage you will be on will be much, much easier. It'll be like finding buried treasure with a map. So on behalf of Mr. Corpy, I am Captain X Beard, reminding you to do your homework. Arrgh!